Hello everybody. Today's a great day to learn organic chemistry. I'm Derek France, and this video will focus on resonance, one of the most important concepts in organic chemistry. Although the topic of resonance is a bit weird and challenging at first, it will become a useful tool that will help you understand and explain many organic chemical phenomena. This video lesson is designed to help introductory organic chemistry students who are learning about resonance for the first time or who wish to review the concept. It is meant to supplement the lecture that you are taking. We will discuss how resonance is a model for understanding delocalization of electrons in organic molecules, and how to use this important tool to draw resonance structures for charged and neutral molecules. We will also learn the effects that resonance has on hybridization and bonding geometry, and discuss important molecular orbital considerations. Finally, we will discuss common errors and how to avoid them. The deeper concepts, such as linear combinations of atomic orbitals and pi systems, are not discussed in this video. Hyperconjugation is also not discussed here. Organic chemistry must be learned with active participation, so you are urged to take notes while watching this video, or to watch it first and then take notes while watching a second time. Be sure to pause throughout the video as needed to write notes, because you won't have time to keep up in real time if this is the first time you are watching. Before looking at specific examples, let's begin by discussing the most important aspects of the resonance model. Delocalization of electrons is, with rare exceptions, a stabilizing phenomenon. In the resonance model, electrons delocalize through p orbitals and pi bonds. By drawing resonance structures, also called canonical forms, chemists can visually describe this delocalization of electrons to explain a variety of observations. It is critical to note that while a molecule that exhibits resonance will have two or more resonance forms, these forms are not interconverting between each other like structures in an equilibrium. Instead, the combination of all resonance forms describes the overall structure of the molecule. Examples will help make this clear. We will begin with charged molecules and then discuss neutral examples. The charged molecules that we will consider will have formal charges on atoms. Recall that, if an atom contains a formal charge, the number of valence electrons on that atom do not match the number that would be predicted in the neutral atom according to its group number on the periodic table. One extra electron will give a formal negative charge, while one less electron will give a formal positive charge. If you do not have a good understanding of formal charge at the moment, I urge you to brush up on that concept before continuing with this video. Because resonance is a description of electron delocalization, one of its primary functions will be to show delocalization of charge. Consider this positively charged molecule here on the left. The positive charge is located on a carbon atom, giving a structure called a carbocation. Carbocation centers only have 3 ligands rather than 4, and the geometry about that carbon atom is trigonal planar with sp2 hybridization. Note that carbocations do not satisfy the octet rule, as they only have 6 electrons in their valence shell. Remembering that resonance occurs through p orbitals and pi bonds, this particular molecule cannot undergo resonance. It can undergo rearrangements like a hydride shift, but this is not resonance, and you'll learn more about this later. Also, this is what is called a primary carbocation, a cation that is attached to 2 hydrogens and 1 carbon. These are highly unstable and generally shouldn't be drawn. Again, you'll learn more about this later as well. Let's take a look now at this example over here. If the molecule has a double bond on the 2 carbons next to the carbocation, in a molecule called the allyl cation, resonance does occur, and this molecule on the right is much more stable than the one without the double bond on the left. The true structure of the molecule is shown here below, and it is symmetric, and it has positive charge density located around this carbon on the left and this carbon on the right. This double bond and the single bond that's depicted on the top actually have the same bond order in the true structure, about a bond order of 1.5. How can this be? The structure drawn above is just one resonance structure. There is another resonance structure that can be drawn like this. We put a double-headed arrow to indicate that these are resonance structures. Using electron pushing arrows, we can arrive at the structure on the right by shifting electrons from this double bond over to the neighboring carbon-carbon bond. Such a flow of electrons forms a double bond on this side and removes one electron from this carbon atom, giving it a positive overall charge. Again, it is important to note that these two structures do not interconvert. Rather, they both describe the overall structure of the true molecule, and because they are equivalent structures, they influence the overall true structure with equal weight. It is important to note what is happening here from a molecular orbital perspective. So here again is our resonance hybrid, which is the two resonance structures shown together. Over here we have the molecule sort of drawn on a side view in order for us to be able to draw in the p orbitals and the pi bonds. So if we begin with this sort of structure here, we can start by drawing in those pi bonds. So we can draw a pi bond, a p orbital right there and another p orbital over here, and then these are interacting in a pi bond. Now the carbocation center is also a p orbital that is vacant. So it's sp2 hybridized, giving this vacant p orbital. Because this is in resonance, it means that this is not a discrete double bond anymore. It's a 1.5 bond where there's an interaction between these two that's a little stronger than a single bond, not quite a double bond, and that interaction also extends equally over to this carbon. So the result of this resonance effect is that now there is bonding across all of these neighboring carbon atoms, and it's about equal, it is equal in all of them. About 1.5 bond, a half double bond. What this also does is it causes the whole structure to be completely planar. This bond right here and this bond right here are also related now by symmetry. They're the same length. This effect of lining up p orbitals and lining up bonds like this is called conjugation. It's a stabilizing effect. And this would be an example of a conjugated carbocation. In most of the rest of this video, we will use line angle structures, such as the one shown here, to draw our molecular structures. In these line angle structures, we don't indicate the hydrogens if they're connected to carbon atoms. If you don't feel comfortable with line angle structures right now, I recommend you go back and check that out again. Brush up on that before you continue with this video. Otherwise, it'll be difficult to keep up. So here we have another example just to indicate that resonance delocalization can spread out into larger systems. You don't just have two resonance structures necessarily, you can have more. So take a look at the structure, pause the video, see if you can draw all of the resonance structures. Okay, I'm assuming you paused. Here they all are. This structure can be delocalized into 4 resonance structures. Now let's consider a resonance-stabilized cation with atoms other than carbon and hydrogen. This structure right here contains a nitrogen atom. Using our electron pushing arrows, we can draw 2 additional resonance structures and 3 total structures. The first process mirrors the process that we saw in the allocation before. The second one requires the lone pair of the nitrogen atom to move onto the carbon-nitrogen bond to form a double bond. This nitrogen atom now has 4 valence electrons instead of 5, giving it a formal positive charge. Note that any atom with lone pairs could participate in this process. Now each of these resonance structures influence the overall structure of the molecule, but they are not equal, so they will have different weights. One of these structures will influence the structure of the real compound more than all the others, and this is called the major contributor. We can use the following criteria to determine the major contributor in a positively charged structure. The major contributor will be the resonance structure in which the octet rule is satisfied for all atoms and possesses the highest number of total bonds. In this set of resonance structures, only one has a full octet on all atoms. Be sure to take the lone pairs into consideration when you're figuring this out. It also contains the most bonds, and that is this structure right here. Whenever we draw a molecule that exhibits resonance, it is best practice to draw it as its major contributor. Although one resonance structure may dominate as the major contributor, all resonance structures are important to describe the molecule's structure and properties. You will notice a few trends as you get more practice drawing resonance structures. When moving charges by shifting the location of double bonds, the charge will move 2 atoms from where it began. When charge is delocalized by lone pairs forming double bonds, the charge moves 1 atom to the atom whose lone pair participates in resonance. Again, let's take a closer look at this cation through the lens of molecular orbital theory, considering the overlap of the p orbitals. The carbon atoms all have partial double bonds as in the previous example. But how should we treat the nitrogen atom? Usually, as shown over here on the right, nitrogen atoms with 3 single bonded groups attached to them have a bent geometry with sp3 hybridization. The structure of this molecule, however, shows a trigonal planar geometry around that nitrogen atom, and this can be described by resonance. In this resonance form up here in the top right, it participates in a double bond. Therefore, we should consider its lone pair, the lone pair of that nitrogen atom, to be in a p orbital that is interacting with the other p orbitals in this pi system. Here we can see that the resonance effect changes the hybridization of this nitrogen atom from sp3, which might be expected, to sp2. A general rule for determining the geometry and hybridization of atoms in structures exhibiting resonance is to consider the geometry and hybridization of the resonance structure in which that atom contains the most bonds. For example, in this molecule, because there is a resonance structure in which the nitrogen up here is part of a double bond, we should consider that nitrogen atom to be sp2 in hybridization. Let's now try to draw all of the resonance structures of this molecule right here, and then try to determine the hybridization of all of the non-hydrogen atoms. Pause the video and give it a try. Okay, I'm assuming that you just paused. Here we go. Here are all the resonance structures that we can draw for this cation. So there we go. We have 4 total resonance structures, 2 of which have positive charge on the oxygen atoms. Which of these do you think is the major contributor? Well, it turns out that these 2 structures are equivalent, and both of these then would be major contributors in this molecule. Now let's try to determine the hybridization of all of the atoms in this molecule. I'm going to draw the molecule one more time, and let's label all of the non-hydrogen atoms. It's always good to draw molecules that have resonance as their major contributors, so here we have it right here. So now what is the hybridization of all of the non-hydrogen atoms? This group, and this group, and this group are all CH3 groups, called methyl groups. Each one of those is sp3. This carbon atom right here, this carbon atom right here, this carbon atom right here, this oxygen atom right here, and let's go all the way to the back. That oxygen atom as well are all sp2 hybridized. They are all going to have a trigonal planar geometry. Now, just to be completely clear here, the oxygen atoms only have 2 groups attached to them and then a lone pair. So in these structures, The oxygen atoms are not exactly trigonal planar, but they will be bent with a bonding angle of about 120 degrees, more like an sp2 hybridized atom than an sp3 hybridized atom. When discussing hybridization of these atoms, we are talking about the overall structure of the molecule, not any specific resonance structure. Nuclei cannot move in resonance structures, remember, and thus the geometry also cannot change. All of the geometric aspects of this structure are the same in all of the resonance structures. In our final example of a positively charged structure with resonance, let's consider the resonance effect of a molecule with a triple bond. In this structure, called the propargyl cation, electrons from a pi bond of the alkyne group can delocalize onto the neighboring single bond. Note that this creates an alene type structure with two double bonds sprouting out of the same carbon, and places the positive charge on the carbon over here. It's important to remember that the atoms do not move at all. When a formal charge is placed on a carbon that is part of a double bond, we call this a vinyl cation. Primary vinyl cations are generally less stable than their alkyl counterparts, but we won't worry too much about determining the major contributor in this case. Now that we have discussed positively charged molecules, let's move on to negatively charged molecules. Just like we did before, let's begin with the simple allyl system. Here is the allyl anion, the negatively charged version. When you have a negative charge on a carbon atom, that is called a carbanion. Carbanions contain 5 valence electrons, not 4, resulting in a negative formal charge on the carbon atom. Note that that carbon atom has 3 atoms attached to it and a lone pair. Just like in the cation, this allyl anion has 2 resonance structures, and we can show them interconverting with electron pushing arrows just like this. If we follow the electron pushing arrows in this process, the lone pair on this carbon atom collapse down into this carbon-carbon bond, and then 2 electrons from this pi bond end up on this carbon atom, giving a lone pair with a negative formal charge on that carbon atom and a double bond on this side of the molecule. The molecular orbital drawing of this molecule shows 3 interacting p orbitals with partial bond formation across each carbon atom, and it looks a lot like the allyl cation, just the negatively charged version of that. Now, remembering how hybridization is affected by resonance, what would the hybridization of each of these 3 carbon atoms be? Because each of them are involved in double bonding in at least one resonance structure, all 3 carbon atoms are sp2 hybridized. Now let's test our knowledge by trying to draw all of the resonance structures for this molecule shown here, including all of the correct electron pushing arrows. Pause the video, give it a shot. Okay, I'm assuming you paused the video and gave it a shot. Here I'll show you all the resonance structures for this molecule, including the electron pushing arrows. And there you have it. You get 4 resonance structures in this system, and here's how you should show the electrons moving around that system with electron pushing arrows. Now let's consider resonance in a negatively charged molecule that has an atom other than hydrogen and carbon. This molecule right here has an oxygen atom. We can move the electrons around just like we showed before, and we can have them end up on the oxygen atom. Let me show you what I mean. So we end up getting 3 total resonance structures, and one of them has the negative charge on the oxygen atom. Now we can see that these resonance structures are not equal. They're all different structures. So let's try to determine the major contributor. Using the criteria that we used before, such as which structure has fulfilled octets and which structure has the most bonds, we will see that all of these 3 have filled octets, and the number of bonds hasn't changed throughout these structures. So in order to determine the major contributor of a resonance stabilized anion, we use the following criteria. The major contributor is the resonance structure in which the negative formal charge is on the most electronegative atom. And in this case, oxygen is more electronegative than carbon, so this right here is the major contributor. In negatively charged systems with resonance, note that the charge always moves two atoms from one resonance structure to the next. Let's now use our understanding of resonance and remember that resonance is a stabilizing phenomenon to try to answer the following question regarding acidity of an organic molecule. Right here on top we have ethanol, and we can see that deprotonation of that ethanol can occur, and the pKa associated with that deprotonation is 16. Down here we have a molecule called phenol, which is another type of system that has an OH bond called an alcohol. And in this case, it's much easier to remove that proton. The pKa is 10. And remember that pKa is a log scale, so it turns out phenol is actually 1,000,000 times more acidic than ethanol, not 6 times more acidic. So let's come up with a resonance-based explanation for this huge difference in pKa. I'll give you a moment to think about it. Pause the video, consider this, and think about why this could be the case using resonance. I'm assuming that you stopped the video and gave this a try. Let's look at this a little further. So if we're talking about resonance, consider ethanol up here. In ethanol, on this side of the equilibrium and the ethoxide after deprotonation, no resonance is available to this molecule. But in phenol, resonance is available after deprotonation, especially. That's what matters here. So take a look at this negatively charged oxygen atom, and let's see if we can draw resonance structures. It turns out we can. Pause the video, see if you can draw them all. Okay, here they are. Okay, there we have 4 resonance structures in this negatively charged molecule. And remember, resonance is a stabilizing phenomenon. So this molecule having access to all these resonance structure stabilizes the anion, and because the anion stabilized, it makes it more easy to lose that proton, giving a lower overall pKa. And one more thing to think about is that this structure, the original one, is the major contributor because the oxygen atom has the negative formal charge. However, those other 3 structures, despite not being major contributors, still have a huge effect on this molecule that reduces that pKa value. Now we're going to move on and take a look at some neutral molecules that exhibit resonance. One of the classic examples is benzene, shown here. This molecule appears to have 3 single bonds and 3 double bonds throughout the ring system. But in reality, it has 6-fold symmetry, and all of those CC bonds have the same bond order, about a 1.5 bond. Resonance can easily rationalize this observation by shifting all of those double bonds. We can get an equivalent structure that has all of the double bonds now in the same location where single bonds were in the structure on the left. So the real overall structure of benzene looks like this, where those dotted lines just show a 1.5 bond. Benzene is also commonly represented with a circle in the center. From a molecular orbital perspective, benzene is a flat molecule that has 6 p orbitals all interacting with one another. As you continue to study organic chemistry, you will learn more about the properties of benzene and how it has a specific characteristic called aromaticity. Now let's move on to a different type of neutral molecule that has a different type of resonance structure, a charge-separated resonance structure. Here's a very common compound that you're going to see in organic chemistry labs. It's called acetone, and it has this carbon-oxygen double bond. That's called a carbonyl group. And that carbonyl group has in it a charge-separated resonance structure that we can talk about. Let me show you what I mean. 2 electrons from this pi bond can end up going on the more electronegative oxygen atom, giving us this resonance structure right here. So when this happens, we have 2 lone pairs in the original structure. Now we end up getting 3 lone pairs in the structure on the right, with a negative formal charge up on that oxygen, and we have to keep a charge balance in this overall structure because it is neutral, so we put a positive charge down here on this carbon atom. So here's an example of a charge-separated resonance structure. Now, is this something that we should worry about at all? Well, let's consider something. The dipole moment of isopropanol, which I'll draw right here, which has a single carbon-oxygen bond, the dipole moment goes up in this direction, and it's about 0.86 dBi. So, a decent dipole. Acetone, on the other hand, has a dipole moment that goes in the same direction, and it's much larger. So let's draw that arrow a bit bigger, the dipole moment, and it turns out that's about 2.4 dBi. So nearly 3 times the intensity. So that enormous dipole moment is in part coming because of this charge-separated resonance structure. Now, when we're dealing with neutral compounds that have charge-separated resonance structures, the major contributor will be the one that has the least charge separation. So based on that definition, our original structure over here would be the major contributor. Okay? Now, that doesn't mean that this is unimportant. Even though it's a minor contributor, you can see the effects that that minor contributor has on the overall structure and properties of this molecule. So let's consider this molecule. It's like acetone, but it has a double bond over here with another carbon coming off of it. Here's a neutral molecule that will have charge-separated resonance structures as well. The first one will look a lot like the one that we drew in acetone, where 2 electrons from this pi bond end up going onto the oxygen atom. So there we have it. And now you can also see that this kind of looks like a carbocation. It's not really, because there's a negative charge that's canceling it out to make it neutral. But this carbocation-like center, at least, can have another resonance structure by participation of electrons of this alkene that's over here, giving us this structure. So now we have 3 resonance structures shown here. Let's consider what this molecule looks like from a molecular orbital point of view. So if we look at this from a molecular orbital point of view, all of these atoms that are participating in resonance have aligned p orbitals, and the structure on the left, having the least amount of charge separation, is the major contributor. So this double bond is going to be pretty much double bond alike, with a little bit of reduction in that double bond character. And then between these 2 carbons, which is a single bond in the major contributor, there's going to be some double bond character resulting from this resonance structure over on the right. So we can show like a little dotted line there just to indicate some double bond character as well. So this is another situation in which we have a conjugated system. And when you see this carbonyl group with 2 carbons coming off of it, that's an example of a ketone. So this would be specifically a conjugated ketone. As you continue your studies in organic chemistry, you will learn how conjugation can affect some spectroscopic properties of functional groups in IR, infrared spectroscopy. So look out for this when you move on to that topic later on. Moving on, here is the structure of what we call an amide, or sometimes pronounced amide. It is a functional group that has a carbonyl group right here and then a nitrogen connected to it. The geometry of that nitrogen atom is completely planar with sp2 hybridization. It's not bent sp3 hybridized like you might expect it to be. The nitrogen is connected to 3 different atoms and it has a lone pair. So you may expect sp3 hybridization with bent geometry, but nope, it is trigonoplanar with sp2 hybridization. And the reason for this, you guessed it, is resonance. So let's draw an important resonance structure for this molecule that is charge separated. Okay, there we have it. So this structure over on this side is charge separated, so it's not the major contributor, but it is still a critically important resonance structure that describes a lot of the properties of this molecule. It describes the geometry around the nitrogen atom. The geometry or hybridization of each atom in a resonance hybrid like this is determined by looking at the resonance structure that has the most bonds connected to that atom. So for example, the nitrogen atom, because of this resonance structure, will be sp2 hybridized. The oxygen atom, because of this resonance structure, will be sp2 hybridized as well, although that's difficult to say experimentally because it's only connected to one other atom. But we could predict that it would have an sp2 hybridization. Another important structural feature of this molecule that can be rationalized by this charge-separated resonance structure is the fact that this bond right here between the carbon and the nitrogen, it's somewhat double bond in nature. It actually doesn't rotate very fast. It involves a lot of energy compared to a normal sort of formal single bond to rotate around this bond right here. And that will have important implications when you learn about NMR spectroscopy later in this course. Some neutral molecules that have resonance structures can only be drawn with charge-separated states. These include ozone and nitrous oxide shown here. Take a look at these. Might not be a bad idea just to make sure you understand why each of them have the formal charge that they do, just for some practice. Finally, let's consider one more type of neutral molecule, an organic radical. Radicals are unpaired electrons, and they can delocalize through resonance like positive or negative charges in a molecule. Here is the allyl radical. Like the allyl cation and allyl anion, this radical has 2 resonance forms, shown here. Drawing the electron pushing arrows for single electrons is a little bit different than for an electron pair. First, we use one-headed arrows for each electron. I'll show you how that works right now. Now let's talk about these arrows in a little more detail. This unpaired electron will go into the area here, the bonded area between these 2 carbons. One electron from the pi bond over here will also enter to form a pi bond between those 2 carbon bonds. The leftover electron from this pi bond will end up going on the carbon to the left, giving the unpaired electron on that side. Nitric oxide is another molecule that has a radical exhibiting resonance, and these would be the 2 resonance structures. I'd like to finish this video by talking about a few common mistakes that I see students make when they learn about resonance and when they learn about drawing resonance structures. The first one is drawing invalid Lewis structures. Now it's important to remember everything we know about structure and octet rule and all of that while considering resonance structures. So what's wrong with this first resonance hybrid that's shown right here? Well, if we look at this nitrogen atom in this resonance structure to the right, we'll see that it violates the octet rule by having 10 electrons in its valence shell. Now in positively charged systems, such as carbocations, carbon may have below an octet, it may have a sextet, but you can't go over the octet rule. So if you have a decat like this, that's a problem. So this would be an invalid Lewis structure and therefore not a valid resonance structure. Another common issue that we see is delocalizing atoms. Remember that resonance is all about delocalizing electrons, not atoms. So this process that's shown right here, where the black hydrogen moves from the center carbon over to the right, that is something that does happen in organic chemistry. That's called a hydride shift. That's called a rearrangement, and you'll learn about that later on. But that's not resonance. So it better not be shown with an arrow like that. So that's something to watch out for. Along these lines, one more thing I'd like to say is that be very careful with your line angle structures. Here I have it drawn out showing all the hydrogens, but if you aren't really sure about where those hydrogens are, feel free to draw them in on the line angle structures just to make sure you're not moving atoms around by accident. A third common mistake that I see is introducing unnecessary charge separations. So we looked at a couple examples of neutral molecules that have charge-separated resonance structures. That's fine. But if you already have a charge to begin with, like this structure shown here, don't introduce new charges. So if you're seeing 3 charges in your molecule, chances are it's not a valid resonance structure. Now there are structures out there that are like that, but if you start with a single negative charge, for example, and now you have 2 negative charges and a positive charge, you probably introduce an unnecessary charge separation. And then finally, this is a less of a conceptual issue and just like a note-keeping issue, a bookkeeping, accounting type of issue. It's neglecting to indicate charge, particularly when we're dealing with resonance structures that are line angle forms. So for example, starting with that same material right here, that same compound, that same molecule, if we draw a resonance structure that's completely valid to show these arrows going here, but we stop here without indicating that there's a negative charge on that side, it wouldn't be correct. Because with that negative charge, it indicates that this carbon atom has 2 hydrogens coming off of it and a lone pair. Without that, let's get rid of that charge, this is now a CH3. So it's very important that we don't forget the basic principles of line angle structures and that we don't forget to indicate charges, because this looks like we just somehow threw on a hydrogen atom. Okay, well that concludes this video on resonance. I would like to thank the National Science Foundation for support, and I'd like to give a citation to Wade and Simek, Organic Chemistry 9th edition, the textbook from which I based parts of this lecture. Until next time, this is Derek France. Keep pushing those electrons.